All right, good afternoon, everyone. Welcome to my talk, Kubernetes Fundamentals. Everyone have a good lunch. We're awake, not getting neitis or anything like that. We're good? Okay, cool. So we'll get started. Then the next slide. Excellent. So who am I? Thanks, Paul, for the introduction. My name is Greg Grennlee. I'm a principal DevOps engineer for a company called Insight. We're an IT solutions company. Been there for about 3 years. So we do everything from web application development, AI, machine learning, DevOps engineering. We augment teams or we place an entire team to take on projects. We are hiring, especially for DevOps engineers. So if you're looking, go to insight.com and I think you can go to careers from there. Born and raised in Cincinnati, Ohio. Currently reside in Cleves, Ohio, which is actually west of Cincinnati. A mentor for Perscolas. That's an organization that seeks to train people for entry-level IT positions. Linux enthusiast. I've actually been coming to Ohio Linux Fest, or now Open Libre Free, since 2006. So quite a long time. Comic book enthusiast, Marvel, DC. And I'm also father, husband, and my wife told me not to put her on the spot, so I'm going to do exactly that because this is her first time actually seeing me speak in person, so there she is in the middle. Yay! She'll kill me later. No, she's not. We're going to Ruth Chris, so. All right, so our agenda for today is we're going to talk a little bit about some of the common terms that we use when we're discussing Kubernetes. We're also going to talk about what is Kubernetes, or K8s, or K8s. Why do we need Kubernetes? How does Kubernetes work? So we're going to go over some of the components, some of the objects, and then how do we interact with Kubernetes? So microservices, we're going to go through this whole list of common terms. So microservices are essentially a bunch of small independent services that communicate via RESTful API calls from one another. You have all these microservices and they communicate with each other and they form a bigger app. So anyone who's not familiar with microservices, that's essentially what it is. And the microservices allows you to scale up, scale down, the different components. So for instance, if you have a website that has like a shopping cart, that shopping cart might be a totally different service from the actual front end that's presenting it. So in periods of like high load, you can actually scale that microservice that runs that shopping cart. And that way, you can have these independent components and you can scale one independently of the other. We're going to skip imperative versus declarative and current state versus desired state. I'm going to come back to those. Cloud native. So essentially, cloud native are just apps that are built for the cloud. They're built to actually utilize cloud services. So Azure, AWS, GCP. When you build your apps, a lot of people or a lot of companies are now refactoring these apps to work with these different cloud services. So these cloud services they offer things like database, message queuing services, and things like that. And so when you build a cloud native app, you're building it to utilize these services natively instead of some type of bolt-on component. So immutable versus mutable. A mutable object can be changed after it's created. Immutable objects can't. So if you think about your traditional IT, operations back in the day, you kind of SSH on the servers to make configuration changes. And so Kubernetes will help with that type of thing. And so you don't actually make changes to the server, you make changes to the image. You wind down the servers that's running, you spin up the other ones, and that way you always know kind of what's running because you're not changing it on the fly. So you don't have like this configuration drift that's happening. Containers. Oh, by the way, I didn't ask, does anybody in here actually use Kubernetes? Show of hands. Okay, so a few people. Okay, cool. So containers. Standard unit of software that packages up code, and all its dependencies. Image is lightweight. They share the machine's OS. So, and then the container runtime is the software that's responsible for running the actual container. So you have your container runtimes like Docker, Containerd, And there's a few others that are out there now. But they essentially make sure that these containers are running and that these containers are doing what they say they want to do. So we're going to talk about imperative versus declarative. And I like this analogy here because imperative is more concerned with a series of steps to achieve its goal, and declarative is just you declare what you want. So in this analogy here, you might have, you want some cake, and imperative way is to actually have your recipe, and you list step by step exactly what you need to do. Declarative is just saying, no, I would just want some effing cake, right? And it goes out and it gives you a nice chocolate cake. In this sense, however, it's going to be about spinning up containers and declaring what you want that to look like. All right, so current state versus desired state. And I like this analogy where it uses the nest because current state is what does your environment look like compared to what do you want your environment to look like. So in this analogy here, your current state is 72. You want your desired state to be 68 degrees, right? So you set it, and then if at any time the temperature actually rises above that, then of course the air conditioner kicks in and it sets it to the desired state. So that's the difference between current state and desired state. So what is orchestration? And I grabbed this definition online and modified it a little bit. The arrangement of containers for application and system performance and the planning or coordination of the elements of a situation to produce a desired effect. So essentially, Kubernetes is an orchestration tool for orchestrating containers. And we'll get more into that in a bit. So Kubernetes helps you scale up, scale down, can perform updates, rollbacks. It's orchestrating this whole thing. So it's self-healing, a node goes down, you need to do upgrades. It does all that stuff for you. All right, so what is Kubernetes? So Kubernetes was first open sourced by Google in 2014. It's not the same exact thing that Google was using. It shares DNA with Borg and Omega. It comes from the Greek term meaning helmsman or pilot. It's what's considered or has been considered a data center OS. And I like that term because if you think about what an OS is, it's essentially abstracting away the hardware from the applications that's running on top of it, right? So it governs resource allocations and things like that. So Kubernetes does the same thing, but in the same thing, but with data center resources, right? So you have your operating system defined as system software that manages computer and hardware, software resources, and then this is no different than kind of what Kubernetes does, which is abstracts the compute in your data center, right? So it sits above your cloud-specific platform. So Kubernetes runs on, or each one of these different cloud platforms, such as Azure, such as AWS, they have their own implementation of Kubernetes, which essentially sits on top of their infrastructure and provides you with compute resources and things like that. So why do we need Kubernetes? And I just had a pretty good discussion with a guy out in the lunchroom about this. Chris, is Chris here? Did he come in here? No? Okay, good. All right. So why do we need Kubernetes? Because all these smurfing containers. Like, what the mother smurf is going on? You got Papa Smurf popping over here. You got Brainy Smurf braining. And we need a way to be able to control these containers. Containers are a good way to bundle, run your applications. But in a production environment, you need a way to manage these containers. And since we live in a world where uptime is critical, we need to ensure that there's no downtime. So for example, if a container goes down, another container needs to start in its place. And this is all handled by Kubernetes, right? That's how Kubernetes comes to the rescue. It provides you with this framework to run these distributed systems resiliently. It takes care of scaling and failover for your applications, provides deployment patterns, and more. So for example, Kubernetes can manage a canary deployment for your systems, right? And so what this gives you is online self-healing, speed, safety and reliability, zero downtime updates and rollouts, immutability, and it does this all in a declarative manner. Right. So this part of the talk, I'm going to go over some of the Kubernetes components. These are the components that actually make up the Kubernetes platform. Real quick, so kind of the steps to deploying an app or having an app run on Kubernetes. You write your app as a microservice in a language of your own choosing. You package this service in its own container using Docker files or using a Docker file. So you build the image, you upload the image to a container registry. And then you essentially wrap each of these containers in its own pod, right? You deploy the pod to the cluster via deployment, Daemon Sets, stateful set, cron jobs, and you do this using what's called a Kubernetes manifest. All right, so we're going to talk about the various different components. So on the right-hand side there, you have the Kubernetes nodes. This is the compute that actually runs your workload. And on each one of these nodes, you have a kubelet, and you have kube proxy, and you have the container runtime. So the kubelet is the agent that runs on each node to make sure the containers are running in a pod. And it communicates back to the kube API server. So if there's a pod that goes down, the kubelet is the agent that notifies the kube API that it's down, and then it goes through the whole process of spinning that pod back up. You have your container runtime, which we talked about, which could be Docker, it could be containerd. You have your kube proxy, which is a network proxy that runs on each node, is a daemon set. And that maintains your network rules, allows communications, network communications to your pod, and it uses OS packet filtering, if that's available, and it forwards traffic itself if it's not available. And each one of these nodes actually has its own IP as well. So then you have your control plane, which they used to call Kubernetes master, but now they just simply refer to it as a control plane. And this is the Kubernetes API service, the component that actually exposes the Kubernetes API. And the cool thing about Kubernetes is each one of these components utilizes the API. So it's kind of like they eat their own dog food. And which makes Kubernetes extensible as well. So you can write against that API and you can extend Kubernetes as much as you want to, right? So everything that needs to communicate within Kubernetes communicates via the kube API server. So then you have etcd, which is your key value store used to store all your cluster data. And your etcd should be backed up because that's what stores your cluster's desired state, among some other things as well. So you need to safeguard that as much as possible. Your kube controller manager is the controller of all controllers, right? So I'll be talking about different controllers and what they do, but the kube controller manager actually controls those controllers. So it consists of like several different, what they call control loops, and it watches the API server for changes. So if the API server communicates that there's a change, then it notifies these controllers, and these controllers go out and it does their thing, whether that's spinning up a new pod or placing a new pod or placing a pod on a new node if it's within a daemon set. So it does all those things. Then you have your scheduler, and that essentially just watches for new work and assigns it to the nodes. And then you have your cloud controller, which is mainly used for services or integrations on a cloud platform. So it manages integrations such as nodes, load balancers, and storage that these cloud providers actually provide. All right, so essentially how this communication works is you write your manifest, which is written in YAML. And that's kind of a declaration of what you want. You submit it to the API server via kubectl, kubecontrol, or kubectl. Use any one of those. And then it manually, and that's done usually via automated pipelines. And then the API server then communicates with the various other components. schedules it to run on one of the nodes, and then that node communicates with the API server regarding the status of the pods that are running on that node. So that's kind of the communication flow right there. All right, so now we're going to talk about the K8's objects themselves. The first one, the K8 Smurf object. No, I'm just kidding, this namespaces. So namespaces are essentially a virtual cluster inside of your Kubernetes cluster. It's a way for you to logically separate. You can separate out different types of things. I've seen people separate environments, or based on environments, based on application. And it's just a real good way to isolate each one of these different services that you have running in Kubernetes from each other. And then you can apply, like, rollback, RBAC to each one of these namespaces for security purposes. So if you don't want someone on your team messing with an application that resides in one namespace, then you can set up RBAC to role-based access control to prohibit them from doing anything within that namespace. And you can also limit other things, such as quota levels for cluster resources, like CPU, memory, that type of thing. You can base that off of the namespace as well. So essentially, that's really helpful for preventing this kind of like this cross-project contamination. And since these namespaces, they provide like these independent environments. So that's a way to kind of take your Kubernetes cluster and kind of chop that up even more if you need to. All right, so the first, or I guess the second Kubernetes object we're going to talk about are pods. It's an API object. It's the smallest atomic object, and you really won't interact directly. You won't deploy a pod per se. You would usually deploy a pod within the framework of a Daemon set or a deployment or a stateful set or something like that. If you're working with Kubernetes like in a development environment on your laptop or something like that, then yeah, you probably will deploy a pod or something like that just to play around with it. So in terms of Docker concepts, pod is similar to a group of Docker containers with shared namespaces, shared file systems. Each pod is meant to run as a single instance of a given application. So rule of thumb is one container per pod, although there are things such as sidecars, which allow or gives a pod more functionality. So for instance, if you have a pod and you have a centralized logging system, you might run a sidecar to facilitate taking logs from that pod and shipping it to a centralized logging server. But you rarely create these individual pods by themselves. Like I said, you normally create them as part of a deployment, a Daemon set, stateful set. So this is kind of how it would look like. You have little Smurfs running in each one of these pods, and you can have similar pods running on different nodes. And that is done for, like, if you need to scale out or something like that, and you need your pods to reside on different nodes for fault tolerance purposes. That's essentially how that would look. And so now, pod health, and I thought this was a demo. It's not. It's so pod health and liveness probe. So you want to know when your pod is dead, or if it's not up and ready to receive traffic. So Kubernetes uses liveness and readiness probes to help with that. So the kubelet uses the liveness probe to know when to restart a container. And liveness probes are used to kind of catch like these deadlock situations where application is running, but it's unable to make some type of progress, and so you need to restart that container. And the kubelet uses the readiness probe to know when a container is ready to actually start accepting traffic. And I'll show you some code here in a second. But it's essentially where a pod starts up. There might be some additional configuration that needs to happen, and you don't want to send traffic to that pod before it's ready to actually start accepting traffic. So you can have a readiness probe wait for a certain amount of time before it actually before it actually starts sending traffic to that pod. All right, so that is very small. Okay, that's very big. Cool. So essentially how this works is you have your pod specification here, and this is what this piece of code is showing. And then you have your spec for your container. It's using an image called liveness. And then down below where you see the liveness probe, you can do an HTTP GET to a certain path. And it'll check that to see whether or not that path is up. And if it's not, it will restart that. It'll essentially keep checking on that specific page. And if it's stops responding, then Kubernetes knows to restart that pod. I actually didn't show the readiness probe, but the readiness probe, the YAML looks pretty similar, but it just has some different configurations when it gets down to configuring it to actually say, hey, take this many seconds before you actually start sending traffic to it. All right. So we are going to go into demo stage. You know what? Hopefully I can figure out about bringing this over to here. Not going to work. It's not bringing it over. Hold on. There it is. Cool. All right. Okay. So let me get my. All right. So we are going to first VM into demo 1 pod, and we're going to show you the Kubernetes manifest for the pod. All right. So what you have here is the API version to start it off, and then you specify the kind, which in this instance is a pod. Then you just give it some metadata, and this metadata can be used for different things. In this instance, once I create the pod, you'll actually see the pod being called nginx -pod. I'm giving it a label, and that's going to be useful for when we talk about services. It's essentially how a service finds a pod and knows to associate that service with the pod. And then we give it some specs for the actual container itself, right? So the container that'll be running inside the pod. So you'll have your image, in which I'm grabbing a nginx image. I'm giving it a name. I'm actually specifying resources, which you can do in Kubernetes. So this is good for when you wanted to limit certain services or certain applications from kind of hogging all the resources on a specific node. Because some services actually do that, and so this is a good way and good practice to actually implement this in your teams to say, hey, you have to have resource limits so you're not hogging all the resources. And then we just give it ports to be able to connect to that pod. We want to expose those ports, so that port section actually specifies what ports we want to expose. So that's that. I'm going to close that, and now I'm going to start the pod. So to start the pod, do a kubectl apply -f. -f is for the file, and then demo 1. Cool. So pod is created. So I do a kubectl get pods, and that shows us our pods. All right. So I have nginx pod, the one that we just created, and you can see that the age of it is 8 seconds. And I have nginx curl running because what I want to do is I want to do a kubectl exec, it, nginx curl, bin bash. So that'll essentially allow me to get a bash prompt on that nginx curl pod. Cool, so I'm inside the pod. So now, just to prove that pod is actually running nginx, you know what? Let me do this first, because I want to do a kubectl describe pod nginx curl. All right, okay. So some essential, when kubectl or kubectl describe gives a lot more information about that specific pod. It gives the image ID that it pulled it from. Of course, you can see it pulled it from the Docker registry. It shows you the IP address of the actual pod itself. And it also shows you, I should have done this on Nginx pod, not curl. All right, cool. Similar stuff, but this IP is really what I need right here. So 172.17.0.2, you can see the label, all that good information. And then down here, it actually shows you the events of what happened. So you can see that it started, created the container and started it up. So cool. So let me go back to my command. All right, so now I just want to do a curl 2.17.0.2. Boom. Nginx. All right, excellent. So the demo gods were nice to me today. All right, so let me go back to, okay, presentation. All right, so we're going to talk now about services. So now that we have our pods running around and cutting grass and doing Smurfy things, right, we need a way to be able to access those pods. When a pod comes up, normally you can only access that internally. As you've seen, I just used the IP that it was assigned. But you know, in order to make these things useful, we need to be able to access it publicly, right? So how do we do that? Gargamel, right? He was responsible for trying to expose the Smurfs. Get it? Forget about it. Anyhow, so services to the rescue, right? Each pod has its own unique IP address. Those IPs are not exposed outside of the cluster without a service. So how do we do that? So services allow for your applications to receive traffic, and it's an abstract way to kind of expose these applications running on a set of pods. It's an API object. It provides stable IPs to the pods, provides some a level of DNS as well. And there's different service types. You have your cluster IP, which exposes the service on an internal IP in the cluster. So, I mean, that's kind of useful, but not, it's only reachable from within the cluster. So if we want to expose it publicly, we can do it using a node port, or in which we really don't want to give people access directly to the node. So we usually do it through a load balancer, which creates this external load balancer, and then it load balances across the pods. So essentially how that looks is you have your service, it gets spun up. You have what's called a selector, and that's what the service uses in order to associate itself with the pod. And we set that label within the pod manifest itself. So that's how it knows to say, hey, I'm going to send traffic to these specific pods using a selector. So you can see I have 3 different pods there, but the label on the last one is app Apache and not app Nginx. So it won't send traffic to those 2 pods, or that pod, it will send traffic to app Nginx. And so you have this stable IP sitting in front of your pods where you can send, people can access, and they can get access to the services that's running behind it. So how does this look? Another demo. All right, let's get it. All right, so let's get back to. Why didn't that come up? There it is. All right. And let me get my thing here. All right, so what I want to do now, I want to clear this. So we're going to look at the service YAML. Pretty simple. You same API version. You declare what kind of manifest this is, because that's That's used for the API server itself to determine what to do. So the kind is a service. Give it some metadata, my Nginx service. Once I show you the services, you'll be able to see that my Nginx is the name. I'm going to use a node port for this, since I don't have the capabilities to bring up a load balancer, so we'll use the node port. And then the selector, the app Nginx. So you remember in that pod, use the label app Nginx. So that's how it knows which pod to select. Then we just essentially expose ports on that. So exposing port 443, the target port is port 80. All right, so, okay, let's not do that. All right, so I am going to start up this service. Apply-f demo2. Boom, service is created. That's how quick it is. So I'll do a kubectl get service. Okay, so you can see the my Nginx service is using a node port. It gives it a cluster IP, but we're not going to use that to actually access it. And it's using port 443, but the port that we'll use to access it is actually 3183. So what I'm going to do is let me make sure. Just want to make sure that this. So 99.100, okay, cool. Clear that. So I am going to do just another curl. I'm going to do it to the node port on port, what was, oh shucks, let me get that port back. 3183, okay, so. Curl 8.100 on port 3183. There you go. So that is essentially the service fronting that pod. And you can tell by you look at it, the services uses this concept of endpoints. And that is essentially what keeps track of the pods that come and go, because pods will die and they will come back up. And each time it does that, it assigns it an IP. And so the service itself needs a way to be able to keep track of those IPs. And the endpoint, the Kubernetes object called an endpoint, is actually how it does it. Need to put a get in here. Is it endpoints? Boom. And so you can see that my Nginx service, the endpoint is that you can see for that specific service, the endpoint is actually the IP address of that pod that we spun up, that 172.17.0.2. And if we were to spin up additional pods, which we'll do with the deployment, we'll go back to that and you'll see those additional pods in there as well. So the IPs of those. Cool, so get back to here, get back to the, all right. So the demo gods were once again kind to me. All right, so we're going to move on to a replica set. Replica sets are actually the underpinnings of a deployment, Daemon Sets, and we'll talk about those here in a second. But with replica sets, it fulfills the purpose of creating and deleting pods as needed. Whenever a pod is, whenever you do a deployment, if, for instance, one of those pods dies and the deployment calls for 5 pods, the replica set is actually the underpinning that is actually saying, okay, there's 4 pods, you declared 5, I'm going to spin up another pod. And we'll see that here in a second. But I just wanted to talk about replica sets. You actually rarely ever interact with the replica set. But I just wanted you to understand the underpinnings of the deployments and the Daemon Sets is actually replica sets. So Daemon Sets ensures that all or some of the our nodes are runs a copy of a specific pod. So as nodes are added to the cluster, the pods then are replicated or added to those. As nodes are removed from the cluster, then those pods are essentially garbage collected. And so the usage of a daemon set is if you need to run a particular pod on each one of the nodes in your cluster. So for instance, if there's some type of log collection daemon or something like that that you need to run those on every node. If, for instance, if you want to get logs from that specific node and you want it to get moved to a centralized logging server, you need to make sure that a log collection pod is running on each one of those nodes. You will use a daemon set in order to deploy that. Same thing for like monitoring or something like that. You need a monitoring pod on each one of the nodes. A daemon set is your answer for that. So a deployment is another Kubernetes API object, and it utilizes replica sets. It creates pods in the background. So it enables you to easily move from one version of code to the next version. So it does application rollouts. Deployments are managed by the deployment controller. It builds, like I said before, builds off of replica sets, and its main purpose is for updates, rollouts, and rollbacks. And it also helps with scaling. So you declare how many specific pods or whatever you want, and it maintains that number based on what you declare. And we'll have a kind of solidify that. So you kind of have like, the replica set, which is the underpinning, running, kind of like this control loop, right? They call it a reconciliation loop. And so for a daemon set, as you can see on the left, you need Papa Smurf to run on every single one of those nodes, right? So daemon set is used for that, for that specific purpose. A deployment, however, is just used to kind of run a certain number of pods within that cluster period. So you might not necessarily have all of them running on each one of the nodes. You might have 2 Papa Smurfs running on node 1 and then 1 Papa Smurf running on node 2. And that's defined in the Kubernetes manifest. So this reconciliation loop that the replica sets is in control of takes your declared desired state and your observed current state, and it takes action based on what's going on. So if a pod was to die, it would look at the declared state and say, hey, what's the state of this supposed to be? Oh, you're supposed to have 3 pods? Okay, I'll spin another one up. Ooh, all right. How are we doing on time? Okay, cool. So we're going to do a demo of deployments. Okay, I get my notes up here real quick. All right. Do an LS. Okay, so 3. All right, so this is what the manifest looks like for a deployment. All right, so name the deployment, Nginx deployment. I want 3 replicas, right? My rolling update strategy is to be able to have 2 spin up at a time. And then the selector is the match labels app Nginx. But for my template, I want each one of the pods themselves to have a label of app Nginx. And then my spec for my containers, once again, Nginx 1.16. The port I want to expose is port 80. Simple, pretty straightforward. So kubectl apply -f demo 3. Boom. My deployment is created, so I'll look at the deployment itself. All right, so you can see the name of the deployment, Nginx deployment, 3 of 3, which is what we specified. And then get pods. You can see all 3 pods are running, Nginx deployment, and then it gives it some arbitrary numbers there. Yeah, so that's deployments. Pretty easy, pretty simple. You just scaled your service up 3 additional pods, right? Cool. All right. So let's talk a little bit about Ingress. Ingress is used to expose HTTP and HTTP routes from outside the cluster to services within the cluster. So, you know, we're going up a layer in abstraction, right? So we had our services, which abstracted our pods, and now we have an ingress, which abstracts the services, right? And we do that so that we can write different types of rules. So anyone who's worked with Nginx, it's kind of like a proxy. That's essentially what this ingress controller is doing. It's routing based on, you know, application layer. So, you know, the headers and things like that is what it's going to route using. So ingress can be configured to give services externally reachable URLs, load balance traffic, terminate SSL, TLS, and offers name-based virtual hosting, right? I'm not going to do anything with do a demo with the ingress. That's just to kind of show you kind of, you know, what's possible using the ingress. And the ingress itself is actually made up of 3 different things. You have the ingress object, you have the ingress rules, and the rules is what you use to kind of describe what you want to happen to the traffic. And I'll show you a snippet of code here in a second. And then you actually have the controller itself, and that's the actual proxy that kind of does all the business, right? So kind of how that looks is like this. The API version is obviously different, but then you specify your kind, which is an ingress. That the annotation is telling it to use the Nginx ingress. Rewrite target, and so then you give it your specs, which is your rules, and in this instance, you say anything coming into test path, then let the service test handle that, right? So you can write all types of, you know, complex rules or rules to move traffic to different services that are fronting different pods. So that's essentially what the ingress is used for. How much time do we have? All right. What time is, we have till 1:50 or?
Yeah, we'll try and shut it down at 1:50.
Okay. All right, so I'm not gonna do maybe I'll do a demo. Okay, so config maps are a way to separate the actual code from the configuration of that code, right? So it makes it easy for you to be able to kind of run it makes your code easier to be able to move from node to node, and you don't have to have that configuration embedded right in your code. So the example I like to give, for instance, if you're running your pod, for instance, on your laptop, and maybe you have a backend database that's running on your local laptop, your config maps can actually be used to kind of separate, say for instance, the database target from your code. So you use Kubernetes to spin up this config map, and you can either have it spin up a config map for your local database, or if you're moving it or you're doing it in the cloud or something like that, that database will be inside the cloud. So obviously you want your database connection string, it might be totally different. And so you can use these config maps to kind of separate that stuff out from your code. And then your pod can consume these config maps in a number of different ways. Command line arguments can be the entry point to a container. Environment variables, which is the demo that I'll show you. It can actually be used as a volume, a read-only volume for the application to read. And so if you configure your application to read from a specific volume and read configuration from that volume, you can use it in that manner. And you can write code to run inside the pod that uses the Kubernetes API. And then secrets are essentially the same thing, but it's for secrets. I don't recommend, I mean, it utilizes, it's used in the same type of way as a file in the volume or environment variable. I don't recommend using Kubernetes Secrets, it's better to use something that, something like Vault, HashiCorp Vault, or Azure Key Vault Flex Volume, because the secrets are actually stored in plain text in etcd. And from a security standpoint, anyone who has access to the Kubernetes API can essentially grab those secrets from etcd. And also, if you're storing this in, you're in manifests too, anyone who can read those manifests can essentially read those secrets, which is, I don't know kind of why they did that, but yeah, so do a real quick demo, hopefully. Oh. Yeah, I got a few minutes. This is the last demo, so I smurf to you, demo gods. All right, let's see. So there is the config map. Okay, so I want to take a look at the config map itself. All right, so essentially what I'm doing here is I'm just declaring some data in the config map. So kind fit config map, giving it some metadata, and then I'm saying, the data that I want is just key value pairs. Color, purple, hair, fairly nice, text mode, true. Pretty simple. So I will go ahead and create that. Config map. All right, that's created. Now, I want to utilize that, so I'd have to spin up a pod that is going to utilize it. So I will show you that config map. All right, so a lot of this stuff is you've already seen from a pod, but here's where it gets interesting is around here. I'm declaring an environment variable. I'm giving that environment variable the name of example key. I'm referencing the key map, the config map that I created, and I want the value of that key value pair of color. So what we should see once we echo this environment variable is we should see purple, the value, right? So, oops. All right, so ctl apply-f config map. All right, so cube ctl get pods, cube ctl get pods. All right, so I have so I'm going to ctl exec, come on, fingers, T, core, fig map, and bash. Oh, what does it say? Oh, okay, so it doesn't have bash on that. So I actually have to do just a shell. Boom, okay, cool. So now I will do an echo of that. What the heck do we call that? Sample key? Is that what we called it? No, shit. Oh, I spelled that wrong. There you go. Demo's complete. All right, how much time? All right, one minute. So, all right. So then, real quick, how do we interact with Kubernetes? I've already said. Can anybody guess what that is? Kube cuddle? I thought that was funny. Ice cube cuddling, come on, man. So, various ways of interacting with Kubernetes. Kubectl is the client side that interacts with Kubernetes API. It uses this kind of nomenclature, so kubectl, the verb, the object type, the object, and you've seen me use kubedescribe, kubectl get, and then delete will delete whatever object that you created. Create will create the object, and then apply will actually, so if you've already created something, you just apply if you made a change or something like that. and it'll create that change. All right, and last but not least, here's some resources. Kubernetes docs are very good, very solid. Minikube is what I used in this demo. It spins up a one node cluster, Kubernetes cluster for you to play around with. Of course, don't use it in production. Kubernetes Up and Running is a really good book. I think they have a new version out for that. If you want to use Kubernetes with multiple nodes in a cluster, labs.playwithk8s.com is a really good one. It's an online way to mess around with Kubernetes. And then the Kubernetes cheat sheet is pretty good. And that's it. That's my talk. Thank you. Sorry I didn't have time for questions. I do have time? Okay. Sorry I don't have time for questions. No, I'm just kidding. Anybody have any questions? No? One? Okay.
I have two.
Yes.
I'll do one overview and one pretty technical. What's your experience in using the cloud providers in Kubernetes, GCP, AWS, or Azure come to mind?
Right.
I was wondering just your random thoughts on their implementation of Kubernetes.
I've always had a positive. I've used AKS for Azure, and a really positive experience. I mean, it takes away a lot of the hard work that you have to do in order to set up a Kubernetes cluster. The management plane is essentially operated by the cloud platform itself. And so that takes away a lot of the complexity that you have to deal with. And essentially, you kind of just, you utilize their service. They take care of the scaling and things like that. So yeah, I've had a positive experience.
Okay, I had another one.
Yeah.
So technically, I was following your second demo.
Okay.
And
Service
you had
one?
node port, and you had a cluster IP and a port 443. Could you have curled that cluster IP with 443? And if not, why? And if so, why wouldn't you have done that?
So I'm trying to think. Where was that one?
Demo two,
So
node port.
the node port one. I think I tried to use 443. Because when you use a node port, it assigns an arbitrary port to utilize on that node. And so in that instance, it assigned that 30 whatever to use.
Oh, okay.
And that's the one that you essentially kind of have to use. Okay. So I didn't actually try 443. Or maybe I did and it didn't work.
All right.
I can't remember.
You didn't during the demo. I was starting to wonder
Say
why.
that again?
I'm sorry. You didn't during the demo. I was
Right.
starting to wonder why.
I'm pretty sure when I ran through the demo before, I might have tried to use that and it didn't work. I was like, oh, okay, it assigns this and you kind of have to use that port. So,
Okay, thank you.
oh, no problem. Anyone else? Excellent. Oh, got one more.
Just a quick question about the scaling that you keep referencing.
Yes.
So when you've created your deployment and you say, I only want 3 pods with this particular service running,
Right.
and you've given them a set determined amount of compute resources, is the scaling that's taken care of by these cloud providers that just creates another node? And then,
So,
I'm just trying to understand that relationship of the scaling
Right,
versus
right.
the services.
right. And from that aspect, if you start running up against like resource constraints, and I think Azure used something called scale sets. And you can say, oh, if it's running up against a certain amount. I guess what I was saying with that is you don't have to go out yourself and build another node. Azure will take care of that for you. You specify that within the scale set, and you can say, okay, I'm reaching a certain number of this resource constraint. I'm going to increase my scale sets, and Azure will then. But from the pod standpoint, the pods themselves, you have to specify in your manifest, in the deployment manifest. They don't do what's called horizontal scaling in that manner. You manually have to specify that. But there is something called horizontal pod auto scaling that you can integrate with Kubernetes, and it'll take care of that that auto scaling from a pod standpoint itself. So you give it like whatever resources that you want it to act on, and then it'll scale out those pods across the nodes. The nodes themselves would then have to be scaled out if you reach a certain resource constraint there. And I think with Azure, you normally use scale sets in order to scale those out. Anyone else? Excellent. Thank you. Appreciate it.